In this video, we're going to talk about the Friis transmission equation and the radar range equation. These are both two versions of pretty much the same thing, and it's just a measure of if I transmit this much power with this antenna and I receive with this antenna, how much power will I get at the receiver? Fundamentally, in both cases, that boils down to the received power is equal to the effective area of the receiver times the incident radiated power density, that's watts per square meter, times the polarization loss factor, like that. Technically, this could be interpreted as a statement of either the Friis transmission equation or the radar range equation. It's just not very useful in this form. So the way we have to make it useful is by breaking down this effective area of the receiver and the incident power density to tell us more about the properties of the receive antenna and the transmit antenna. That effective aperture of the receive antenna includes a bunch of important stuff. It's got the receive antenna radiation efficiency. It's got the receive antenna directivity at the angle from which the incident wave is coming. It's got a factor of lambda squared over 4 pi, which is what turns it into effective area. You've seen that before when we talked about the directivity. And if there are mismatch losses to include, those would be included here too. So we would also include the matching efficiency, 1 minus gamma squared for the receive antenna. All that stuff gets included in the antenna's effective area. In terms of the incident power density, we've got the transmit power itself, the transmit antenna efficiency, the transmit antenna's matching efficiency, the transmit antenna's directivity along the direction looking towards the receiver, and a 1 over 4 pi r squared for free space path loss. You might recognize 4 pi r squared as the surface area of a sphere of radius r. So that 1 over 4 pi r squared describes the effect of the power that is being transmitted spreading out into a larger and larger area. This directivity describes its dependence on angle, on direction. And these efficiency terms tell you how much of that power is not actually making it into the radiated power. So if I put all this together, I get that the received power is equal to lambda over 4 pi r whole quantity squared, receive antenna efficiency, receive antenna matching efficiency, receive antenna directivity, in the direction that the receive antenna is looking, polarization loss factor, transmit antenna directivity in the direction that the transmit antenna is looking times transmit antenna matching efficiency times transmit antenna efficiency. Did I get everything? Yes. This is the entire, oh, and I forgot an important factor, the transmit power itself. So that's the entire Friis transmission equation. It's possible to break all these terms down. If I lump all of this stuff together, that's the receive antenna realized gain. If I lump all of this stuff together, that's the transmit antenna realized gain. You can write this equation in larger or smaller ways depending on which quantities are most convenient for you to express it in. But that is the Friis transmission equation with all of its parts. And that is written for the situation where you have one antenna over here, and maybe another antenna over here. I'm going to make it a dish. We don't do enough dishes in this class. There we go. And maybe my transmit antenna is transmitting and my receive antenna is receiving in a line of sight kind of way. This describes a lot of communications links. But what about a more radar-like scenario? What if we have a radar link where we have a transmit antenna and then we have some kind of target, and that transmitted wave bounces off the target and then hits a receive antenna? That is represented by the radar range equation instead. Now, the first part of this equation is going to work out to be exactly the same because, there we go, like that. I'm writing it this way, which is a little bit more complicated than necessary because this is technically a bistatic radar situation. If I had the receive antenna and the transmit antenna in the same location, like I'm drawing in red, that would be a monostatic radar situation. The monostatic radar situation is a little bit different because the angle and distance variables are all the same. For bistatic radar, it's different distances. So let me write this down for the radar range equation is going to, so I'm going to write down a monostatic radar range equation. So let's pretend that this bistatic radar did not happen. First of all, the incident power on the target is going to depend on the transmitter power, the transmit antenna efficiency, the transmit antenna matching efficiency, and the transmit antenna directivity, and the distance to the target. Now, that incident power density hits this radar target, and the target scatters it. The target acts like an antenna itself. It sort of absorbs some of that power and then re-radiates it back out. The amount with which it does that is called its radar cross-section, and we use the Greek letter sigma for that because even though we've already used that for conductivity in electromagnetics, we're using it for radar cross-section as well because I guess there just aren't enough Greek letters. technically, the radar cross-section is a function of both the incident angle and the receive angle, because if you look at this from a different direction, you might get a different amount of energy back, because it's not going to come out equally in all directions. It's going to kind of be really squiggly like that. But since we're doing a monostatic radar range equation, we're not going to worry about that right now, and we're going to just say that the radar cross section is a number. Now this whole thing tells you the amount of power that is coming back towards the receive antenna. But this radar target acts like another transmitting antenna, which means that that needs to get multiplied by a 1 over 4 pi r squared factor, because it needs to spread out spherically from that radar target. And then when it gets to the receive antenna, it needs to actually be accepted and received by the receive antenna. So there's going to be the receive antenna efficiency, the receive antenna matching efficiency, the receive antenna directivity, the polarization loss factor is a little bit more complicated here, because it's possible for the target to radiate a different polarization than the one that the transmitter radiated, but we're going to just put in the polarization loss factor the way that it normally is, with the understanding that this little t on the PT is now not the transmitter polarization unit vector, but the target polarization unit vector. That whole equation tells you how much power is received by the receiving antenna in this little picture up here. That's the radar range equation.